Okay, we are now live again on YouTube. Sorry for that. Okay, so as I was mentioning, we have seen basically two categories of um reinforcement learning algorithms that are model-based and model-free reinforcement learning algorithms. And we have spent most of the time focusing on model-free reinforcement learning. In model-free land, we have seen three groups of algorithms that are value-based, uh, policy gradient, and actor critic. Now, what's the main difference between those? Sorry, I can't move this, looks like, but anyway. Okay, yes. Okay, what is the main difference between these? Value-based methods make use of a value function or an action value function more precisely, and on top of this action value function, a policy is computed as a greedy policy, a policy that um, maximizes this value function. And that's the case of algorithms that we have seen, where we have this trade-off between exploration and exploitation, thanks to the use of an epsilon greedy policy. An epsilon greedy policy is a policy that is uh, greedy with probability 1 minus epsilon, with epsilon being very small, and it is instead randomly selecting an action with probability epsilon. So policy gradient methods instead can make use of a value function, but a policy is directly represented. So there is a policy that is learned um, sort of independently as a different item that is separated from the value function. So we directly learn a policy in these algorithms. There is not anymore the argmax computation with respect to the value function, but the policy is directly learned and represented independently of the value function. And actor critic methods actually try to bring these two words together, um, because they actor critic methods still use still use a policy directly represented, but also make use of a value function uh, mm, that is used at every step. So the learning is actually very dependent on a value function, although there is also here, there is not a specific step where we do an argmax with respect to the value function. Among value-based methods, we have seen basically, let me add some other text here. Let's choose this. So we have seen Monte Carlo methods, temporal difference methods. Actually, let me leave some space for this. Temporal difference methods, and step TD. Right now, we have also seen that um, these algorithms can be all these algorithms can be categorized in on policy and off policy methods, where so there is also this other categorization where we have on policy for some reason it's not okay, on policy and off policy. So what's the main difference between on-policy and off-policy methods? The difference between on-policy methods and off-policy methods is the fact that while in on-policy methods, we learn about the same policy that is collecting data for us. In off-policy methods, we can learn about a different policy while collecting data with the so-called behavior policy, the policy that generates the data. And actually, this on-policy and off-policy categorization does apply to all these algorithms, but also to we'll see while reading some papers, but also to actor critic methods, because the way the value function is learned makes the difference in this categorization. So we have seen both on-policy Monte Carlo methods, where we have been directly using the data collected from the policy, and off-policy Monte Carlo methods, where we use importance sampling, where the importance sampling is giving us basically some information about how relevant that specific transition or that specific sequence of transitions is relevant for the policy that we're learning about, compared to the policy that generated the data. So if the data is very rare for the on policy, for the target policy, for the policy that we're learning about, then we give it a high weight. If it is instead a very low weight in the case that the target policy doesn't care a lot, and instead a high weight in case that the target policy cares a lot. So let's write down some formulas here. So the general formula for the update in tabular length, right? In tabular length is the following. Let's call it Q, because we mostly use Q, gets the current Q plus alpha that multiplies some target minus Q. So this is a general error correction formula where alpha is the gain, if you want to look at this in a control-like fashion. And this is the error. So we're correcting the error in moving towards some target, right? So we're trying to reduce the error by correcting our prediction or in the direction of the gradient, and moving a small step in that direction. And this is the general formula in tabular length. Specifically, this is for value-based methods. So what we have to do in each of these approaches is just replacing this target and with the correct one that we're interested in. So for example, let's look at some of these. If we, okay. So if we're interested in Monte Carlo methods, let's consider the on-policy case. In Monte Carlo methods, we typically have a target that is the G, which is the return. Now, the return, as you remember, is just, let's write it down, it's just simply the sum of discounted rewards. So the sum of discounted rewards means that, sorry, let me reduce also the size of this. There is a way to do this. Format, font size, 18, okay. So the sum of discounted rewards. Now, let's look at some temporal difference methods instead. In temporal difference land, we have seen algorithms that are on policy and off policy, like SARSA and Q-learning. So we'll see the target for SARSA, which is reward plus gamma, which is the discount factor, as usual, which is the discount factor that multiplies the Q of S prime A prime, where S prime comes and is the next state, and A prime is sampled from the policy. Okay, well, pi is the policy. So what's happening here? We are taking the new reward that we're collecting in the state that we are in, and basically we are making a small correction in the direction of the information that we just get in this single time step, which is the reward. So we use the single label that we get at every step, which is the reward, and we use this in order to correct our prediction. Actually, this, in order to be 100% correct, would be 1 minus done, 1 minus termination. I will not use this notation over here just to not make it too verbose, but you just need to remember that if you are in a terminal state, you don't need to sum anymore the value of the next state, because the next state does not exist here. So the target for Q-learning instead, Q-learning is again the reward that multiplies the discount factor and the maximum over the actions for Q as prime A. So now we're moving again in direction of correcting this single time step prediction using the reward information, but in the look ahead step, which is where we are considering the information regarding the next step, we're not taking anymore into account the policy distribution, the action policy distribution, but we are considering as our target policy, right? This is why it's of policy, the optimal policy. So while here we are evaluating the current policy, here we are directly evaluating the optimal policy. So this is why this is on policy, and this is why this is off policy. Okay. And step TD is basically an intermediate between temporal difference methods and Monte Carlo methods. In step TD, basically we behave like Monte Carlo methods for a certain number of steps, and then when reaching the end step, we use a bootstrapping step, which is basically relying on the Q function for the next nth state. So this is basically unifying temporal difference and Monte Carlo methods. And I didn't mention in here another algorithm that we have seen, which is expected SARSA. Expected SARSA is doing something slightly different. So SARSA, still using the reward, but in this case, we are then using the probability of every action in the next state that multiplies the Q of SA, where here we are summing over all the possible actions. So if I can set where I write, it looks like I cannot edit this object over here for some reason. So let me write it down again. I can remove it at least. Let's get rid of it. And let's write it down again. T of expected SARSA equals reward plus sum over all actions of uh, pi of s prime that multiplies q of s prime a. So this is another approach, and the main difference between these and this kind of algorithm is the fact that SARS and Q-learning use sample updates. So they just use information from the sample they would get. For example, SARS is using a sample update. So A prime is sampled from the policy distribution, while expected SARS uses the full policy distribution in order to do the update. So as you see, all these algorithms share the same structure, and then the only thing that is actually making a difference is how you compute the target. Now, uh, I have been focusing basically on tabular methods, but this applies also to methods when you use function approximators. Specifically, if we use a function approximator, then and we are maybe correcting the weights of our value function, the general formula for the update is the following. I will write FA in order to represent the function approximator. So now we'll talk about the parameters. So if we have, actually, let's write it down more clearly. So if we have a function that is a value function that is parameterized by some parameters w, then we can update these parameters by using the following update. So the new parameters are the previous parameters plus, again, some alpha, so which is, again, the step size, or more famous as learning rate, alpha, where we have our again, error that we're going to make explicit here as the target minus the current prediction, which is then multiplying the gradient of V. So this is the overall formula, and this is V or Q, it's the same. So you can replace V or Q independently. So this needs to be a differentiable function, of course, and for example, it can be a function that is something like this. If you have a V that is of this form, that is V equals W transposed that multiplies X, where X are the features. So these features are computed as we said in our 2 classes ago, as we said 2 classes ago, from the state by using featureizations like, for example, radial basis functions, style coding, and so on and so forth. Note that this is a linear function in the features. Again, this is transposed. This is the weight transposed that multiplies the features. So it's just a linear combination of the features where the weights are learned. Of course, you can use something that is nonlinear. You can use a neural network, and so on, so forth. Okay, this is in the space of value functions. Now, if we move in the length of policy gradients, we have also said also here, basically, if we look at algorithms like reinforce, we are in Monte Carlo land. Monte Carlo land means that we have to wait the end of the episode. We do our data at the end of the episode when we can compute the full return for every state that has been visited by the policy. So in this specific case, for example, we can compute again the return as usual, and then update our policy, which will be parameterized by some parameters theta, which I want to repeat, it's a requirement in order to use policy gradient. The policy needs to be directly computed and represented in a differentiable function. It needs to be differentiable. So if we have a policy that is differentiable, then we have basically we're using some function approximation also there, where we can assume that the parameters are the parameters theta for our policy, and these parameters theta will be corrected with the usual formula, where we're using our learning rate, which we can set for this specific um, problem, that multiplies our target, and uh, this multiplies the gradient of the logarithm of the policy. Okay, this is the general formula. Now, if we look at reinforce, our target is the uh, return. Return. Now, if you let's use the same notation, t equals g, the return. Now, if you recall what's happening in policy gradient methods, the target is basically what we are trying to maximize. So here there is not really an error, but we are trying to maximize a performance function. This performance function coincides with the value function, and the return in expectation corresponds exactly to the value function. So by sampling trajectories using Monte Carlo sampling, so executing the policy in our environment, we collect a bunch of trajectories, and these trajectories will be used in order to compute the return. And again, the return in expectation will correspond to the value function. And that's why we can do something like this. Then we have seen also another version of reinforce, where we have our target being computed using a baseline. So the target will be, in this case, G minus B. So this baseline corresponds basically to removing some, this baseline corresponds to, helps in removing some variance from our computation. Just because, the value function corresponds to the average of the value of all the actions. So basically, we are shifting our all the values that we're getting from the actions in a space where they are centered in 0. In active critic, we have seen just one method, but again, this is still in policy gradient land, except that now we are updating the the value function and the policy in a TD like manner. I want to go just back to a second to the reinforced with baseline, and here we are using of course, the value function. So we are updating the value function using a Monte Carlo method, using a function approximator. So using this formula over here with this target over here. Actually, I just remembered that I need to create a Slido code for you in order to ask me questions. So give me just a second. I will write on the thing on the whiteboard directly the code for you. So new Slido RL 23 and schedule event. So present in your tab, and the Slido code is the following. I'm going to write it down here this is the Slido code. 21. If it allows me to write 2 1, okay, 5 5. For some reason it stops. It doesn't allow me to keep writing. 2 1 5 5 6. Okay, this is the Slido code. So if you have questions regarding this, please do not hesitate asking these questions. In TD-like manner, which means that for actor critic method, for one-step episodic actor critic methods, which are the ones that we have seen, we are going to do the update using a value function that is computed again using this formula, where the target is computed using this other formula. Actually, we're using directly value functions, so not Q, but directly V, which means that we are going to use not for one-step episodic actor critic methods, we're not going to do SARSA or Q-learning, but we're going to do TD0, which means that our target in this case will be for the value function will be the target will be the reward plus gamma that multiplies V of S prime, and for the policy we're going to have a target which is going to be computed in the same way. So this target is going then to be applied in this formula where we're going to update also our policy. So this is basically unifying for you everything that we have seen in one single slide, where we are moving from tabular length to functional approximators, and we are just moving between these algorithms very simply just by changing the targets or one single formula, moving from tabular to functional approximators, which also brings us in policy gradient and actor critic land. So I want to pause it here and see if there are any questions. I would be glad to see any comment or question on this that should be hopefully helping you. I want to just add that in actor critic methods, there are, among actor critic methods, there are a lot of approaches, including papers that we're going to read or that you're going to implement, like soft actor critic or SAC, proximal policy optimization, which is also known as PPO, and other very famous algorithms. So most of the algorithms that are at the state of the art nowadays are actor critic methods, but also, there are algorithms that have been used very successfully, like the deep Q networks that have been the algorithms that allowed DeepMind to achieve superhuman performances in Atari games. So again, this was nothing else than a combination of Q-learning with functional approximators that are neural networks and just some other tricks that basically allow to decorrelate data and achieve some more stable learning. So this is really what you are looking at currently. So I'm going to shut up for some minutes just to check if there are some questions, and then we're going to maybe talk a bit on model-based land, and otherwise I'm gonna move also to the example code. Uh, okay, I don't see any question, which means that everything is super clear, I guess. And actually, I want to mention that you should exploit this opportunity that you have, because I mean, you have no reason of being shy because you're not in person. So if you have questions, you can use this anonymous Slido thing to ask any question, which is even dumb, but at least can be answered and can be removed from your doubt. So if you have questions, please do ask questions, because it's an opportunity for you. It's not something that you do for me. Um, what does tabular mean? So yeah, okay. So tabular means that we use a representation for the q or the value function that is a table. So if you look at all the codes that I posted on Classroom, all the Python notebooks that I posted on Classroom, there I'm using a representation for the Q function, which is a table, and that's the tabular approach. If you're using instead a function approximator, like a neural network, to represent your Q function or your policy, then you are not using a tabular approach. Mm? Okay. So in model-based land, we have seen that basically not only we interact, the agent interacts with uh, the environment in order to collect transitions and learn a key function or a value function or a policy and so on and so forth, but also it does learn, it uses this information, the agent uses this information in order to learn a model. Um, okay, so let me just stop the sharing for a second. Let me share it because something was broken. Okay, now we also learn a model here, and we use it for planning. Now we have basically seen two kind of approaches for planning: offline planning and decision time planning. So in offline planning, we have seen agents like Dyna agents, or specifically DynaQ, where the what's happening basically is that we use transitions that are collected by the agent in order to do Q learning, and at the same time, every transition is assumed to be deterministic, and it's stored in a table, and from this table we can basically do some sampling of the transitions that we have seen, and we can do, for example, 20 sampling steps, and in these 20 from these 20 samples we apply Q planning, which is basically nothing else than using the formula that we have here for Q learning, but done on this tabular model that we have created. Um, among decision time algorithms, instead we have seen rollout algorithms. MCTS, Monte Carlo Tree Search, and UCT. So rollout algorithms, we have seen that basically they in every time, so decision time planning occurs every time that we need to take an action. So every time that the agent has to take an action, the agent creates in his mind all possible scenarios, evaluates them, and then takes the decision of which action should be executed. Specifically, rollout algorithms in this simulation part where the agent is thinking about what is the best thing to do, try all the available action from the current state, and um, so they try one action, they execute what is the so-called rollout policy until they reach a terminal state, or they decide to, or there is a truncation from the algorithm in the depth of this search, and they back up the information that they collected, which is the information that they collect. It's just the return from the current state by trying the action that they want to try and then following the rollout policy. They do the same for all the actions a bunch of times so that they can build basically a queue function, right? They can build an expectation of the return that you would get from the current state by taking every each possible action that is being considered and following the rollout policy. So by collecting a bunch of trajectories for each action, they can estimate the queue function and then use the queue function to take the best action and then discard everything. Everything gets discarded. Monte Carlo tree search is slightly different because Monte Carlo tree search, first of all, goes a bit more in depth, where from the current state, a tree is built, and in this tree, there are 4 steps that occur. First of all, there is a selection step where a certain path basically is selected. Then there is an expansion step where if an action has not been selected yet, then the agent expands this tree, adding the new state that occurs by executing this new action. Um, and then a selection step where the tree policy is being used. And finally, in this expansion, there is also a selection, of course. And then after this, there is the rollout. So the rollout part where the rollout policy is executed until termination or until truncation. And after this, finally, there is a backup as done for the rollout algorithms. In differently from rollout algorithms, Monte Carlo tree search algorithms makes you make um, use of these 2 policies, not only the rollout policy, but also the tree policy, and they can store the tree, reuse the tree, and also store and reuse the value functions, depending on the specific implementation. UCT is just a variant of Monte Carlo tree search, where the tree policy is an UCB1 tree policy, which is, as we have seen for bandit problems, it's using some optimism, where basically if you didn't visit some state for a bunch of time, then this I mean, basically if you visited a certain state for a lot of times, then you are not exploring a lot that state. Otherwise, you're trying to explore states that you didn't visit a lot. Okay, so there is a question. Let's see. I didn't get clearly why we have to differentiate between tabular and functional approximator. You need to differentiate between those because the update formula changes. So this is the formula that you get for tabular cases, and the functional approximator is the following. Also, functional approximation typically brings some further complexity. So typically, if you can use a table, then you can have a complete representation of your state space and action space, which means that you don't have approximation errors. In function approximation, you typically have approximation errors, but at the same time, a table cannot generalize among similar states, while function approximators can generalize between, among similar states. That's why you differentiate between those, and that's why you may or may not want to use one or the other. So if you are using if you're dealing with a small grid board, then you don't need a function approximator. You can use a table very likely. But if you're dealing with Atari games, for example, or more complex situation like in robotics or stuff like this, where you cannot certainly represent your state space and action space as a table, then you want to use a function approximator. And I hope this clarifies your question. If not, please ask more details. Okay, so if we are clear on this, I will switch then to looking at our code. But again, let's first wait maybe a couple of minutes more and see if there are other questions. Okay, while you think whether you have other questions or not, I will share the screen um, with the code that we're going to look at. So share screen. Can you see this? Can you see my screen with this small car moving up to the hill? Okay, great. So I'm going to show you how to do Q-learning on a very simple domain on which belongs to the OpenAI Gym set of domains. Specifically, it's a famous domain known as Monte car, where the task of this car that starts from this location is to learn to go up over the hill and reach this location over here, reach the flag. So I've created a collab notebook where basically we are doing Q-learning using a neural network. So as I was mentioning, the goal is reach the top of the hill, and the state that the environment returns to the algorithm is the position and the velocity of the car. The actions that are available to the agents are pushing left, not pushing at all, so doing nothing, and pushing right. So beyond this part where I'm installing some libraries which are useful for the just for running everything on Colab, which I mean, you'll need those only if you're doing things on Colab. Otherwise, let's focus on the actual code. So here there are a bunch of imports, and again there is also some wrapper over here where we are I'm using this just to create a video that can be visualized on Colab. So again, this part is not relevant to the purpose of the algorithm itself. So if you use Colab and you want to see the video that is being generated by the environment, then you need to wrap your environment inside the monitor, and this monitor needs to record your video as an MP4 and then replay that. So that's everything that is happening. Otherwise, let's look at the actual relevant part. So the relevant part here is that we are creating an environment. I'm creating a mountain car environment, and I'm just using fixing the seed. So if you don't know this, when you run experiments, it's very important to fix the seed and allow in this way for reproducibility. The seed is basically controlling the random numbers that are being generated. So if you are using always the same seed, you will see always the same sequence of random numbers that are generated. Of course, if you want to do some experiments, you need to select a bunch of seeds, not only one, but maybe 10 or 15, or actually to get some statistical significance, at least 30 seeds in order to compute the mean and the variance of your results. Anyway, so this environment is characterized by an observation space and by an action space. As you have seen in your homework, this is what OpenAI gym environments typically contain. So the observation space has a low and high. So the observation space has a size of 2. Has a size of position and velocity, so it's a size of 4. And then it has a low and high, and yeah, and similarly the action space, there are just a certain number of actions that correspond to going left, going right, or doing nothing. In here we don't need to look at the detail of the code, but I'm performing, you can look at this at home, but here I'm performing the tile coding. I'm creating tile coding representations for my environment. So the tile coding, as you remember, is a sort of the discretization of the state space in the form of a grid-like scenario where you have some offsets, and these offsets allow generalization between different states. So if you have states that fall in the same tile, then they will share some feature, and these shared features will basically allow for generalization. So here I'm doing nothing else than computing my tile coding, and here I'm just using some code to get vectors of zeros and ones, where one is turned on when the feature is when the state belongs to that feature, and vice versa. At zero if the state does not belong to that feature. So on. Up to this point, everything should be pretty clear. Nothing should be very strange, because we're just creating code for pre-processing our state. Because as I mentioned in our whiteboard before, if you're using a function approximator for your Q function or value function, then you want to create some features on top of your state, and these features are then used for the learning process. Then here I've created my TensorFlow model. Here I'm using TensorFlow 2, as everybody should be using if you're using TensorFlow, but also other frameworks like MXNet, PyTorch are very good and commonly used both in industry and in academia. Anyway, here I'm just creating my model, and this model takes as input the tiles just to know the shape of the input. So I'm creating an input layer where I'm setting what is the input shape, and then I'm passing the a list that corresponds to the number of units that I want for every layer, and then the number of actions. So basically I will have a certain number of hidden layers in the neural network with a certain number of hidden units, and an output layer where the number, an output layer whose dimension is the same of the number of actions. Why? Because this is a Q function. So being this a Q function, I want to have something like this. This is the neural network. It takes in the state, or actually the features that are computed on top of the state. And then I want this neural network to emit the Q values for every possible action, right? Because we say the Q values are computed for every possible action. So that's what is happening over here. And then this is just in the initialization. I'm creating my model, and then what means calling this model? It just means passing my input towards in the input layer, passing this output of the input layer through every hidden layer, and finally computing the output by means of the output layer. Note that in these hidden layers, for every hidden unit, I'm typically using an activation, which is a relu activation. A relu activation, if you don't know that, is an activation function where if you have some uh, if your input to the activation function is of this kind, then everything which is below 0, so this is x, and this is y, everything which is below 0 gets remains fixed at 0, and then otherwise you have a linear function like this. Okay, so basically it's canceling everything which is below 0. Otherwise, everything is represented as a linear function in the ReLU. So this is a nonlinearity in the neural network. So if you have an activation like a ReLU, then you have a nonlinear neural network. Okay, so then I'm initializing my model, the Q function as my model that takes an input details. I'm saying I want to have 2 hidden layers with 256 hidden units each, and then the output should correspond to the number of actions. And then I'm using an optimizer, which is an optimizer like that we're calling Adam specifically here. It's just a different version of a stochastic gradient descent, where there is some notion of momentum, but again, it's just stochastic gradient descent that you should have seen by now with Professor Yock. Hopefully, at least I'm not, I mean, I hope I'm not saying anything very unknown to you. So we can look at how the type coding process works, but again, it's just a discretization. We have seen ideally what's happening over there in the slides. I can also share that again with you if you don't remember that. Then let's go through the actual learning algorithm. So I'm pre-processing my state by getting the type coding, and then given I'm getting a bunch of arrays, I'm just flattening the array over here. And that's it. Predict is just calling the Q function. Policy is just doing the argmax of the Q values, right? Predict is calling the Q function. So vals are all the Q values. I'm doing argmax to compute the action with probability in basically 1 minus epsilon, and otherwise I'm selecting a random action. Okay, so this is how I compute my policy. Then for every episode in the number of maximum episodes that I fixed to 200, I reset my environment. I get my current state, I process my current state, and then until termination, what I do is I execute some actions. I collect, basically, I pass in the featureized representation to the policy. The policy returns an action. Here I'm setting epsilon for exploration, given that this is epsilon greedy to 0.1. And then this, by executing this action, by calling step function in the environment, I execute the action, and I obtain a new observation, a new reward, and a new termination. So the next state representation, the new observation representation featureized, is called next feature. Then what I do, and here is the TensorFlow auto differentiation is coming to help us a lot, is I just need to compute the error function, and then everything else, which means all that small formulas that allow us to compute the update for every weight in the neural network by using backpropagation, are automatically computed. So everything that I need to do here is just tipping the gradient, starting my computation. So this means that I'm going to compute the Q values for the current state for every for the current state for every action, and then filtering the action that has actually been selected, so the only one that I care about. Then I compute my target. So this is the current prediction, right? So this is the current prediction, QSA, right? So let's add a comment over here, QSA. This is the target. I'm blocking the gradients over here because on the target I don't want to do any. I don't want to perform any update on the value function based on this prediction that I'm doing internally here. This is just used to compute my target. The target should not be used. Should not lead to any correction in the value function except when computing the loss. So the target is computed as the reward plus 1 minus termination that multiplies the maximum over the Qs in the next state. So this is basically, let's add the comment. This is reward plus 1 minus done that multiplies the maximum over Q S prime A, maximum for over all the actions. Then the loss is just a mean square error. So the error squared and then mean. So the mean square error. And then we collect the gradients that we collected for every trainable variable in the Q function. We apply the gradients and that's it. So I do this for these 200 episodes. I do learning for 200 episodes using this epsilon at 0.1. That is my exploration phase. And then I evaluate my policy, which means I reset the environment once again after all the 200 episodes are finished. And then what I do is I see every observation. I collect every observation. I pass the observation to my, featurized observation to my policy, with epsilon being 0 this time because I'm evaluating my policy. I'm not doing learning anymore. I don't need to explore anymore. So I set epsilon to 0 here, and then I execute all the actions, and then I do rendering. So rendering will record this video for us, and you will see that at the end of this, you will have the learning successful. So the car is capable of going up the hill. Okay, so I went quickly through this. I will share this Python notebook with you on Classroom. Let me see if there are questions regarding this. So no, this is not the low and the high. It's not that you are giving this. This is given by the environment to you. So it's telling you what is the smallest and the highest observation that you can get. The smallest and the highest observation that are in the observation space, meaning that every other observation will be contained between the low and the high value. For example, if you have an environment, not if you give, but if the environment has a low, which is 0, and a high, which is 3, this will mean that every observation that you will be able to get from the environment will be between 0 and 3. So if you are implementing the environment, then you are selecting those, and you are choosing the correct representation for your state, and then you're selecting what is the low and the high according to what you're actually trying to represent. Okay, so hopefully this is clear. Let's go to the classroom and see again, look again at the slides for the so if we look at the slides for the function approximation, this is how tile coding is. It's a form of coarse coding where the state space is divided, however, in tiles. So if you have a continuous state space, it's like you're applying a sort of grid on top of it. But actually you have more than one tile, which means that you have 3, 4 tiling, each with different offsets. So it's like you have a bunch of grids, one over the other. Okay, so the overlapping of these tiles correspond to the generalization capability of your features. And this is represented in here. So if you have asymmetric offsets in your tiles, typically you can generalize better than compared with symmetric offsets. I mean, I don't think it's worth spending the time understanding how this is computed in here. You should just spend some time at home looking at this. I don't think it's beneficial for anybody except, I mean, as you can see, I'm using the notion of offset. I'm creating a linear space between, I'm just dividing linearly the space using a certain number of bins that I'm selecting. And that's it. Other questions? Any question? If not, we can close it here because that's everything I wanted to bring on for this meeting, for this lesson. Sorry. For the next lessons that we'll be discussing some paper. As I mentioned, I'll probably post the reference to the paper like a couple of days before on Classroom. So actually, I have a couple of persons that have booked some time for office hours on Thursday, if they are available over. I mean, if they're connected now, maybe we can directly spend some time discussing your questions right now. Otherwise, we can close it here. I will anyway stop the YouTube streaming right now. So let me first stop sharing.